IR experiments get messy fast when baselines, rewrites, and rerankers live in separate scripts. PyTerrier gives you one reproducible pipeline to compare BM25, RM3, and SPLADE fairly. This is the workflow you'll know how to run when we're done, which compares three rankers with a fixed seed and reports the top choice by a shared metric. I'm Professor Pi, teaching search and IR with simple Python. Researchers and engineers spend too much time gluing tools together. One script builds an index, another runs a baseline, a third wraps a neural model. Reproducibility breaks, and comparisons become unfair. Success here means you can rerun the same inputs, swaps, and metrics and get a clean answer about what actually helps. PyTerrier gives you a single pipeline abstraction. It makes indices, retrieval, query expansion, and reranking composable. That means the same query and judgments run through different systems in the same way. You get apples-to-apples comparisons with far less boilerplate. The idea is simple. Start with a tiny corpus and one query. Run BM25 as a baseline. Then swap in pseudo-relevance feedback. Then add a neural sparse reranker. Finally, run an experiment that reports a shared metric so we can pick a winner. Now, we'll set up that tiny corpus and the Terrier backend. This snippet initializes PyTerrier and prepares a tiny corpus and one query. The call to PT_init starts the Terrier backend so we can index and search. The variable docs is a list of small, readable documents keyed by docno and text, giving us a compact toy collection. The variable queries is a single-row pandas data frame matching PyTerrier's topics format with QID and query columns. Keeping everything in memory here makes it easy to reason about later ranking changes without juggling files. The final print confirms that the working set is loaded, so subsequent steps can safely build on it. Next, we will build a minimal index and run BM25 to get a clear baseline. This example builds a minimal Terrier index and runs a BM25 search. The IterDictIndexer consumes the in-memory docs and writes a small on-disk index referenced by IndexRef. The batch retrieve object, BR, performs first-stage retrieval using BM25 over that index. Calling transform on BR with the query's data frame produces scored results, which are then sorted by score within each query. Taking head 1 keeps only the top document, so the outcome is unambiguous. The printed doc identifier and score show BM25's best match under these settings, giving us a clear starting baseline to compare against later techniques. Now, we will add a simple query expansion step to see how feedback changes results. This code adds RM3 pseudo-relevance feedback using PyTerrier's RM3 transformer. The object RM3 reads top documents from the BM25 index and selects FB terms from the top FB docs to expand the original query. The QE data frame therefore contains rewritten queries that mix original intent with feedback terms estimated from likely relevant documents. Passing QE through the same BM25 retriever BR yields a fresh ranking that reflects the expanded vocabulary. Increasing FB terms usually broadens recall but can add noise. Increasing FB docs smooths estimates but may dilute focus. The printed top document and score show how feedback influences ranking strength for this query. Next, we will plug in a sparse neural reranker to see how learned expansions reshuffle the top list. This snippet applies a SPLADE neural reranker via PyTerrier SPLADE's SPLADE factory. The factory loads the Naver SPLADE co-condenser ensemble distill model, and SPLADE builds a reranking transformer that scores BM25 candidates using sparse expansion signals learned by the neural encoder. The composed pipeline pipe first retrieves with BR. Then rescoring happens in place with SPLADE, keeping the interface uniform. Transform executes the entire pipeline, and we sort to expose the strongest candidate. Model choice affects both accuracy and latency. Larger variants may boost re-ranking quality at higher cost. The printed document and score reveal how SPLADE reshapes the top of the list within a consistent pipeline. Now we will bring everything together and run a proper experiment with judgments. This example runs a unified PyTerrier experiment to compare 3 pipelines. The Krell's data frame encodes graded relevance for our query, enabling proper evaluation. The list pipes collects BM25, RM3 plus BM25, and BM25 plus SPLADE pipelines, so they share topics and judgment data. PT experiment executes each pipeline consistently and computes nDCG cut 3, returning a tidy data frame aligned with names. Pulling the metric column into S makes it easy to report aligned scores in a single, readable print. If you expand to more queries, variance will stabilize and differences will be clearer. The printed nDCG values directly quantify performance, closing the loop on a reproducible comparison. In a real project, you swap the tiny docs for your document collection and feed the same trial pipelines. The same experiment pattern scales to a corpus of thousands or millions when you replace the in-memory index with a persisted one or add an ANN step. The code keeps the comparison logic identical, so you can trust the measured gains. Recap. PyTerrier pipelines make retrieval, feedback, and re-ranking composable and repeatable. Use this when you want fair comparisons between baselines and learned re-rankers without scripting chaos. One caveat: neural re-rankers add latency and may need a candidate filter to stay practical. For the next step, tune one parameter across the pipelines, for example BM25 K1 and B, and rerun the experiment to see which setting generalizes best. If short practical IR helps, subscribe and watch the IR videos.